with the next talk by Teo. I can read from there. Teo Gil Moreno de Mora Sardà, who is a PhD student in Paris and Barcelona. And he's going to talk to us about the decomposition of complete three manifolds of positive scalar curvature with quadratic decay.
Thank you for the introduction and also for the opportunity to give a talk. And as Lucas said, today I wanted to present a result, which is a joint work with Florent Balachef and Stéphane Saboureau on the topology of manifolds admitting metrics of positive scalar curvature. So the first that I want to start by introducing the central notion of this talk, which will be a scalar curvature. So in order to do so, let's start as we always do, which is by taking M, a Riemannian manifold, of dimension n. And throughout all the talk, I will consider that all manifolds, I will assume that all manifolds are orientable without boundary and complete with respect to the Riemannian metric. So, as you may know, scalar curvature is one of the different notions of curvature that we can define from the Riemann curvature tensor, and actually is the weakest of them all in the sense that it carries the least geometric information. So there are multiple ways to define it. Scalar curvature is a function, a real valued function on our manifold, and today I'll give two equivalent definitions for it. The first one is, as I've said, directly from the curvature tensor, and scalar curvature at a point it can be defined as the sum of all sectional curvatures over a collection of orthogonal two planes tangent to the manifold at the point x. So here, the EIs denote an orthonormal basis of the tangent space at the point x. But equivalently, there's an equivalent definition which has a more metric flavor. And to do so, we consider the geodesic ball centered at x of radius r. And it turns out that if we compute the volume of this ball for infinitesimal radii, this volume is approximately the volume of the Euclidean ball, the Euclidean ball of the same radius. So here, Bn denotes the volume of the unit Euclidean ball. But actually, if one develops this expression in terms of the radius, we will see appear an error term at order 2 in the radius, which, up to a dimensional constant, coincides with minus the scalar curvature at the point x. So equivalently, one can consider or define the scalar curvature as a distortion in the volume of small geodesic balls. And more precisely, if the scalar curvature at a point is positive, that means that small geodesic balls have less volume than their Euclidean counterpart. And if the scalar curvature is negative, that means that the volume of such balls is larger than the Euclidean counterpart. And in dimension 2, the scalar curvature coincides with twice the Gauss curvature, so it's one of the possible generalizations of the Gauss curvature to higher dimensions. So the question I'll be interested today is the following, which are the three-dimensional manifolds that admit a complete Riemannian metric G, verifying that its scalar curvature is everywhere positive. So these manifolds in the literature are called PSC manifolds from positive scalar curvature. And this question was asked, for example, by Yao in his problem section that has been mentioned before. It's the problem 27. And before starting to discuss the different partial results, the conjecture, this question in full generality is still open, but there are some partial results. And before talking about them, let me give some motivation why we should be interested in such manifolds. And I'll give two results. The first is a result of the 1970s by Kasdan and Warner, who proved that actually any manifold admits a metric of negative scalar curvature. So if we have a closed manifold of dimension at least 3, obviously this is not true in dimension 2 because of Gauss-Bonnet formula, but in dimension at least 3, they proved something actually more general. If you have a function on your manifold M which is negative somewhere, so at some point of the manifold, then there always exists a Riemannian metric realizing the function f as its scalar curvature. So in particular, there's no obstruction in admitting metrics of negative scalar curvature, whereas the positive scalar curvature case is much more interesting. And one of the second result I want to talk is what was originally a conjecture, which is known as the Gerock conjecture, which states that the n-dimensional torus does not admit a metric of positive scalar curvature. And this is no longer a conjecture. It was proven also in the 70s by Shen and Yao, who used the famous minimal hypersurface method, and independently by Gromov and Lawson using the Dirac operator method. So compared to the negative scalar curvature case, there are some topological obstructions to admitting metrics of positive scalar curvature. So during the rest of the talk, I'll discuss this question, and I'll start by discussing the case of closed PSC free manifolds. And let me start by giving a list of easy examples of PSC three-dimensional manifolds. So here, the easiest of the examples, as you may guess, is the three-dimensional sphere, which with the round metric has constant positive scalar curvature. From the three sphere, we can construct other families of examples just by taking quotients of it, is what are called spherical manifolds. So as I've said, they are manifolds of the form S3 quotient by gamma, where gamma is a subgroup of SO4 which acts on S3 freely by isometries. So which kind of manifold can we encounter here? If gamma is the group of two elements, here we have the real projective three-dimensional space. And more generally, for cyclic, finite cyclic groups, here we encounter a very important class of manifolds in three-dimensional topology, which are called the length spaces. And actually, the list doesn't finish here. There are other classes of spherical manifolds, but these are actually they are classified, but these are the most famous ones. And the third example of spherical manifold is the product of the two sphere with the circle, which with the Riemannian product of the round matrix also has constant positive scalar curvature. And also in the early 80s, it was proven by Shen and Yao and independently by Gromov and Lawson, that whenever you have two Riemannian, two PSC manifolds, and you take their connected sum, what you get is, again, a PSC manifold. So the property of being PSC is actually preserved by the operation of taking a connected sum. This theorem is known as the surgery theorem, and actually it's more general. It holds for any dimension starting from 3, and for more general types of surgeries, but in particular it works for the connected sum. And with this theorem, we can actually enlarge our list of examples by taking connected sums of these types of manifolds. So any manifold of this form will also be a PSC manifold. And recall here that since the connected sum is associative and commutative, and the 3-sphere acts as a neutral element, these are all the types of manifolds that we can construct from this list. And actually, Gromov and Lawson, in 1983, they proved that we don't have other examples of closed orientable PSC 3-dimensional manifolds. So what they proved is that if you have a closed orientable 3-dimensional PSC manifold, manifold, M is PSC, even only if M is homeomorphic to a connected sum to a finite connected sum of spherical manifolds and S2 cross S1 products. So let me comment a little bit on this result by Gromov and Lawson. It relies on a very classical theorem in 3-dimensional topology, which states that any closed manifold can be decomposed in what we call prime manifolds, and which is known as and actually this decomposition is unique up to permutation of the factors and adding S3, so some spheres. And this is known as the Kneser-Milnor theorem. And moreover, the closed orientable 3-dimensional, the closed orientable prime 3-dimensional manifolds are also classified. And in order to fully classify them, we need the resolution of the elliptization conjecture by Perelman. So here, I should cite also Perelman's work. After whom, so any manifold, any closed orientable manifold can be decomposed as the connected sum of spherical manifolds, S2 cross S1 products, and aspherical manifolds. So manifolds whose universal cover is contractible. And the actual contribution of Gromov and Lawson to the proof of the theorem was to rule out the appearance of such factors. So Gromov and Lawson, what they actually proved is that we cannot have aspherical factors in this decomposition. So actually, a consequence of this theorem, also by Gromov and Lawson, is that aspherical 3 manifolds are not PSC. So in particular, so this was also how they solved Geroch conjecture. In particular, the torus is not a PSC manifold. Also, hyperbolic manifolds are not PSC. And this statement is actually open for general dimension, and recently it was proven by Shodosh and Lee for dimensions 4 and 5. But in general, starting from dimension 6 is something that is not proven yet. So with this result of Gromov and Lawson and the result also of Perelman, we conclude the classification of closed PSC 3-dimensional manifolds. And now I want to discuss the case of open PSC three-dimensional manifolds. So non-compact manifolds with empty boundary. And the first thing that one should do when studying these manifolds is to enlarge the notion of connected sum, to generalize the notion of connected sum to be able to modelize manifolds admitting an infinite number of terms, an infinite connected sum of terms, of prime manifolds, for example. And the way to do so was introduced by Scott, is what is called an infinite connected sum modeled on a locally finite graph. This is a notion which was introduced by Scott in the 70s. And the construction goes as follows. So fix G, a graph, a locally finite graph, so a graph whose vertices have finite degree. And at each vertex, we assign a manifold. So in general, we can take any manifold. Here, I'll just consider closed prime manifolds, but you can do this construction for actually any kind of manifold. And anytime that two vertices are adjacent, I'll take the connected sum of the corresponding manifolds. So this is the proper notion to define an infinite connected sum, but still is quite a badly behaved notion in the sense that, for example, we don't have an analog of Nézzel-Milnov decomposition for non-compact manifolds. So there's no existence. Not every non-compact manifold admits such a decomposition, and there's no unicity in a reasonable sense. But it was recently proven that if one assumes further hypotheses on the geometry of the manifold, then one can assure that the manifold admits such a decomposition. And this was proven by Wang and by Gromov independently. Who showed that if M is a complete, so not necessarily compact, Riemannian manifold with uniformly positive scalar curvature, so with positive scalar curvature bounded away from 0, then M admits such a decomposition, and the only terms that we have are spherical terms and S2 cross S1 products, where here the connected sum is possibly infinite, modeled on a certain graph. And so with Florent Balachev and Stéphane Saboureau, what we asked ourselves was at which point this hypothesis was necessary. So at which point we could relax this hypothesis and still get such a decomposition. And what we found is the following. So this is Balachev, Saboureau, and myself, that if we have M a complete Riemannian manifold, and so let M be a complete Riemannian manifold, and X be a point on M. If the scalar curvature on M is just positive, but it does not decay too fast at infinity, so we allow the scalar curvature to tend to 0 at infinity, but not too fast, and the scalar curvature decays more precisely almost, or at most quadratically at infinity with respect to the distance. Okay, and here I should say for this inequality to make sense, I should assume that we're looking far enough from X. And for a value of the constant C not too small. So actually, the specific value is 64p squared. Then we still get a decomposition. Then M still decomposes, still is homeomorphic to an infinite connected sum of spherical manifolds and S2 cross S1 products. And so let me finish by stating, moreover, this result is, we found that this result is optimal in the decay rate. So moreover, and this is because the manifold R2 cross S1 is a prime manifold, so it does not admit, in particular, such a decomposition. But yet it admits a complete metric, which is of the following form. So it's something that looks kind of like parabolic in the R2 factor, which has scalar curvature decaying exactly quadratically with the radius, but for a worse constant. So let me discuss in the 3 minutes that I have left a little bit about the proof of this result. So in particular, this result includes the theorem of the result of Gromov and Wang, but actually we used kind of a different approach. The techniques that Gromov and Wang used to prove it are techniques based on the new bubbles. Whereas as we worked, we kind of we worked using something called the fill radius. So we worked using some estimates involving the filling disks of contractible curves of our manifold. And this was done using a theorem by Gromov and Lawson, also from this paper of 1983, who proved that if you have a manifold, a compact manifold, K, let's say closed to simplify, and you have that the scalar curvature is uniformly positive, then every closed curve, which is contractible on K, bounds. So here we have our gamma, and what Gromov, so it bounds at a disk because it is contractible, but what Gromov and Lawson they proved is that actually it bounds a disk not too far from itself. So it bounds a disk in its 2 pi over the square root of S0, where S0 is the lower bound on the scalar curvature. This condition is denoted, or we say then that the fill radius of the curve gamma is bounded by this quantity, this metric quantity. And what we did was to translate, so in particular, a uniform lower bound for the scalar curvature gives a uniform upper bound for the filling radius. And what we did was to adapt this theorem. So from a decay condition on the scalar curvature, we could get a growth condition on the filling radii of curves. So this is actually, you get a kind of like a linear control on the filling radius. And it is actually in this setting that we are able to prove, so in this more general setting that we're able to prove the decomposition theorem. So it actually holds for manifolds satisfying some metric estimate on the filling disks. And actually, just for technical reasons, these curves are not taken actually on the base manifold, but more they are taken on the universal cover, but it's just some technical detail. So yeah, I think that I'll stop here. So thank you very much for the attention, and obrigado. And